Today we discuss about the rank nullity theorem. For that purpose, let us first see what is row, column, and zero space. Row space, if A is any m by n matrix, then the subspace of Rn is spanned by the row vectors of A is called the row space of A. That is, set of all the rows of a matrix is called row space. Column space, if A is any m by n matrix, then the subspace of Rm is spanned by the column vectors of A is called the column space of A. That is, set of all the columns of a matrix is called column space. Third one, zero space or null space of a vector space. The solution space of the homogeneous system of linear equation Ax equal to 0 is called the null space of A. It is subspace of Rn. Some important properties of row and column space. A non-homogeneous system of linear equations Ax equal to B is consistent if and only if B is a linear combination of the column vectors of A, that is, B is in the column space of A. Now, let us define what is the rank nullity theorem or dimension theorem. Relation between row and column space. If A is any matrix, then the row space of A and column space of A have the same dimension. Rank of a matrix. If A is any matrix, then the dimension of the row space or column space is called the rank of A. It is denoted by rank of A. Here, rank of A is determined by what is the dimension of row space or what is the dimension of column space. Nullity of a matrix. If A is any matrix, then the dimension of null space is called the nullity of A. It is denoted by NUL, null of A. Dimension theorem for a matrix. If A is a matrix with n columns, then rank of A plus nullity of A which is equal to n number of columns. Procedure to find rank and nullity theorem. Procedure to find rank and nullity. The rank of A is the number of leading variables in row echelon form of A, and the nullity of A is the number of non-leading variable in a row equivalent form of A. Let us take one example which will clarify all this row space, column space, null space, and rank nullity theorem. Examples on rank and nullity theorem are dimension theorem. Let us take example number 1. Verify rank nullity theorem for the following matrix. B is equal to 1, 4, 5, 4, 2, 9, 8, 2, 2, 9, 9, 7, 1 minus 4 minus 5 minus 4. Let us try to solve this question. We have to first find basis for null space, column space, and row space for the matrix B is equal to 1, 4, 5, 4, 2, 9, 8, 2, 2, 9, 9, 7, and minus 1, minus 4, minus 5, minus 4. We have to, for this purpose, we have to reduce the matrix to its row echelon form. What is row echelon form? It is nothing but we have to first see what is the diagonal element. If we are able to convert all diagonal element is 1 and below all diagonal elements are 0, then that is called row echelon form of the given matrix. We have to try to make all diagonal elements 1 and below main diagonal all elements should become 0. But the condition is we have to only apply row operations. Apply in row number 2 R2 minus 2 R1, R2 minus 2 R1, in row number 3 R3 minus 2 R1, and row number 4 R4 plus R1. Let us check that we are getting correct answer or not. So let me go ahead. Let me write down that matrix once again. Okay. So this is 2, 9, 8, 2, 2, 9, 8, 2. If you multiply this row by 2, we are getting 2, 8, 10, and 8. If you subtract it, this is 0, 1, minus 2, and minus 6. 0, 1, minus 2, minus 6. If we go to the second part, 2, 9, 9, 7, 2, 8, 10, 8. If we subtract it, minus, 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 minus. 0, 1, minus 1, minus 1. And the last part, if we add that, we are getting 0, 0, 0, and 0. So we have this matrix 1, 4, 5, 4, no change in the first row, 0, 1, minus 2, minus 6, 0, 1, minus 1, minus 1, and the last row is 0, 0, 0. Now we have to move the element A to 2. Again, look here. We ask question, is A22 1? Clearly here A22 is 1. With the help of this one, we have to make this one 0 because this is already 0. We apply in row number 3, R3 minus R2. Then the reduced matrix is no change in the first row, no change in the second row. In the third row, 0 minus 0 is 0, 1 minus 1 is 0, minus 1 plus 2 is plus 1, minus 1 plus 6 is plus 5. Last row is already 0, no need to do any operation over here. Now we move to A33. A33 is already 1, and below A33 it is already 0. So no need to do any operation over here. Now here 1, 4, 5, 4, 0, 1, minus 2, minus 6, 0, 0, 1, 5, 0, 0, 0, 0. This is row echelon form of the given matrix because the all column, all the elements of the diagonal are 1 and below 1 all are 0. Now we are positioned to say find out the row space, column space, and null space. B is equal to 1, 4, 5, 4. This is row echelon form of the given matrix. The reduced system of linear equations can be written as, let us convert into the linear equations form. 1x1, 4x2, 5x3 plus 4x4 equal to 0, first equation. Second equation is x2 minus 2x2 minus 6x4, x2 minus 2x3 minus 6x4 equal to 0. Third equation is x3 plus 5x4 equal to 0. Now we have 3 equations and 4 variables. It means that one variable has independent value. Since one variable has independent values, let us put x4. Here the number of unknowns are 4 and the number of equations is 3. So the one variable has independent values. Let x4 is equal to a. x4 is equal to a. Then from equation number 3, x3 plus 5a equal to 0, which gives us x3 is equal to minus 5a. Now we substitute the value of x4 and x3 in equation number 2. Then we are able to get the value of x2. x2 minus 2, x3 minus 6, x4 equal to 0. x2 minus 2 times of minus 5a minus 6 into a, which is equal to 0. x2 plus 10a minus 6a equal to 0. 10a minus 6a is 4a, which gives us x2 is equal to minus 4a. If we substitute the value of x2, x3, and x4 in equation number 1, we have, this is equation number 1. So we have already obtained the value of x2, x3, and x4. If we substitute all these three values, we are able to get the value of x1, which implies x1 plus 4 into minus 4a, 5 into minus 5a, plus 4 into a. x1 minus 16a, 4 to 16a, minus 25a, plus 4a equal to 0. Minus 16a minus 25a, which is equal to minus 41a, plus 4a, which gives us the x1 equal to 37a. Now we are able to say what is the null space. The solution space or null space is given by x1, x2, x3, x4, such that x1, x2, x3, x4 are belongs to real number or real number. What is the value of x1? x1 is nothing but 37a, x2 is minus 4a, x3 is minus 5a, and x4 is equal to a. Now if we take a outside, we can write down 37, minus 4, minus 5, and 1, where a belongs to R. This shows that the set of all solutions of the linear system is the set of all linear combinations of the vectors 37 minus 4 minus 5, 1. This vector is linearly independent and hence these form the basis of null space. Therefore, null space has only one element, 37 minus 4 minus 5 and 1. This vector is linearly independent because it is only one, hence this form the basis for null space. Now let us find out what is the column space. The basis for a column space of B is the column vectors that contains the leading ones in a row echelon form. Now the given matrix is B is equal to 1, 4, 5, 4, 2, 9, 8, 2, 2, 9, 9, 7, and minus 1, minus 4, minus 5, minus 4. And its row echelon form is 1, 4, 5, 4, 0, 1, minus 2, minus 6, 0, 0, 1, 5, 0, 0, 0, 1. Now, what are the leading elements in its row equivalent form? So this is the first leading element. This is second leading one element, and this is the third leading one element. If we see that what is the column in which this leading one are present, this is the first column, this is the second column, and this is the third column. The first, second, and third columns of row equivalent form of B contain the leading ones of row vectors. Therefore, the first, second, and third columns of B form a basis for column space B. Thus, the basis for column space B is given by corresponding column 1, 1, 2, 2 minus 1. Similarly, for the second, 4, 9, 9 minus 4. And for the third, 5, 8, 9 minus 5. This is column space. Similarly, let us try to find out row space. The basis for a row space of A is the row vector that contain the leading ones in a row equivalent form of A. Now the given matrix is this, and its row equivalent form is 1 4 5 4 0 1 minus 2 minus 6 0 0 1 5 and 0 0 0. The first, what is the first leading element? This is the first row, this is the second row, and this is the third row. The first, second, and third rows of row equivalent form of A contains the leading ones of row vectors. Therefore, the first, second, and the third row of A form a basis for row space of A. Thus, the basis for row space of A is nothing but the first row, this is the first row, then the second row, and this is the third row. 1 4 5 4, the first row, second is 2 9 8 2, and third is 2 9 9 7. Verification of rank nullity theorem or dimension theorem. According to this theorem, if A is a matrix with n columns, then rank of A plus nullity of A equal to n. We have null space 37 minus 4 minus 5 1, row space 1 4 5 4 2 9 8 2 2 9 9 7, and column space is 1 2 2 minus 1 4 9 4 minus 4 5 8 9 minus 5. Rank of A is equal to number of elements in row space or column space. So now just look here. In the row space, there are 3 elements, and also in the column space, there are only three elements. And we have already seen that the total number of total number of element in row space and column space both will be same. Our dimension of row space and column space are always same. Now, nullity of A is equal to number of element in null space. So now, in the null space, there is only one element, which is 37 minus 4 minus 5 and 1. Therefore, left-hand side, which is equal to rank of A plus nullity of A, rank of A is equal to 3, nullity of A equal to 1, which is equal to 4, which is number of columns. Hence, rank nullity theorem or dimension theorem is verified for the given matrix. Thank you.